Hello friends, welcome back to my channel. Today I would like to talk about some concepts of organic chemistry. First, let's look into formulae, functional groups, and the naming of organic compounds. Organic chemistry is the study of hydrocarbons and their derivatives. Carbon can form a variety of compounds because carbon is tetravalent. Carbon-carbon bonds can be single, double, or triple. Atoms can be arranged in chains, branches, and rings. Homologous series, a series of compounds of similar structures in which contain the same functional group, all share same general formula. Formula of homolog differs from neighbor by CH2, similar chemical properties, gradual change in physical properties as Mr increases. Functional group, an atom or group of atoms in an organic molecule that determine the characteristic reactions of a homologous series. Alkyl group is a reactive group which is alkane minus one hydrogen. The next topic is hydrocarbons. The simplest organic compounds are composed of carbon and hydrogen and are known as hydrocarbons. There are four types or classes of hydrocarbons. Alkanes contain all carbon-carbon single bonds. These are known as saturated hydrocarbons. Alkenes contain at least one carbon-carbon double bond. Alkynes contain at least one carbon-carbon triple bond. Both alkenes and alkynes are known as unsaturated hydrocarbons. Aromatic hydrocarbons contain a benzene structure. Lewis structures of alkanes look like this. These are also structural formulas. These take up a lot of space, so we use condensed structural formulas. Even simpler than condensed structural formulas are skeletal or line formulas. Different types of formulas are mentioned over here. They are homologous series, name of functional group, structural formula of functional group, displayed formula, skeletal formula, and the name. Continuation of this is here. The next subtopic is systematic nomenclature. Select longest chain as the main chain, other carbon chains as substituent alkyl groups. Give lowest number C in main chain to substituent. If different alkyl groups present on identical position, give simpler alkyl the smaller number. Two or more alkyl groups present, order them alphabetically. If same substituent repeated, use di, tri, tetra as prefix. If a ring of carbon present, use the prefix cyclo. Write position of double bond in alkene. Example, but1-ene. Example of molecules are shown over here. The first one is 2,4-dimethyl pentane. Next example, 5-ethyl 2,4-dimethyl octane. This is 2-butene or but2-ene. Another example is 1,3-pentadiene. This compound is named 4-methyl-2-pentene. Note that the double bond takes precedence in naming. Naming functional group X. X is fluorine, chlorine, bromine, or iodine. Halogens attached to a hydrocarbon chain are named by replacing the INE ending of the halogen name with O. Example, bromomethane, iodoethane, 2-chloropropane, 1,2-dibromobutane. How to name the functional group OH, which is alcohol. Number the longest carbon chain so that the OH group is attached to the carbon atom with the lowest possible number. Name the parent compound by using the alkane name and replacing the E ending with an ol ending. Examples: methanol, ethanol, 1-propanol, and 2-propanol. Naming functional group O, which is ether. Ethers are commonly named by naming each group attached to the oxygen followed by the word ether. If one group has no simple name, the ether can be named as an alkoxy derivative of the larger group. Examples: dimethyl ether or methoxymethane. Next example, methyl ethyl ether or methoxyethane. Another example, diethyl ether or ethoxyethane. How to name the functional group carbonyl compounds. This includes several types of compounds: aldehydes, ketones, carboxylic acids, esters, and amides. The functional group is shown over here. The first one is aldehyde, which has functional group CHO. While naming aldehydes, number the longest carbon chain starting with CHO group. Name the parent compound by using the alkane name and replacing the E ending with an L ending. Examples: methanol is methyl aldehyde. Ethanol is ethyl aldehyde, also known as acetaldehyde. Second is ketones, functional group COO. While naming ketones, number the longest carbon chain starting so that the COO group is attached to the carbon atom with the lowest number. Name the parent compound by using the alkane name and replacing the E ending with an ON ending. Examples: propanone, dimethyl ketone or acetone. Another example is 2-butanone, which is methyl ethyl ketone. The next one is carboxylic acids, which has a functional group COOH. While naming the acids, number the longest carbon chain starting with the COOH group. Name the parent compound by using the alkane name and replacing the E ending with an oic acid ending. Examples: methanoic acid, which is otherwise called formic acid. Second example, ethanoic acid, which is also called acetic acid. The next one is esters. An ester is formed from the combination of a carboxylic acid and an alcohol. They are often highly aromatic compounds and are used for flavors and fragrances. Functional group is COO. While naming esters, it's usually named by naming the R group from an alcohol as an alkyl group first, followed by the acid name, the RC group with ending O8. Esters are often called by their common names. The next functional group is amide, which is CON. Amides are commonly named similar to a carboxylic acid, replacing the oic acid suffix with amide. Example: formamide or methylamide. The second example is ethanamide or acetamide. The displayed and skeletal formulae of benzene is shown here. How to name aryl compounds. If only one alkyl group is bonded to a benzene ring, we do not have to include a number in the name. This is because all 6 carbon atoms in the ring are equivalent. Example: methylbenzene, 1,2-dimethylbenzene and 1,4-dimethylbenzene. Characteristic organic reactions. Homolytic and heterolytic fission. Organic reactions involve the breaking of covalent bonds. There are 2 ways in which a covalent bond can be broken: by homolytic or heterolytic fission. Homolytic fission is the breaking of a covalent bond in such a way that one electron goes to each atom, forming free radicals. As you can see here, AB undergoes homolytic fission in presence of UV light, forming free radicals A and free radical B. Cl2 molecule breaks to form Cl free radicals. A free radical is an atom or a group of atoms with an unpaired electrons formed from the homolytic fission of a covalent bond and is very reactive. Heterolytic fission is the breaking of a covalent bond in such a way that both electrons go to the same atom, forming cation and anion. As you can see here, AB, the bond is shifted to B, forming A plus and B minus. Or if the electron is going to A, it forms A negative and B positive. Example is shown over here also. Nucleophiles and electrophiles. A nucleophile is a species which contains a lone pair of electrons and is attracted to regions of positive charge or electron deficient sites. They are often negatively charged or carry a partial negative charge. Some examples of nucleophiles are NH3, Cn-, OH-, Cl-, Br-, and H2O. Nucleophiles will attack electron deficient regions. Example, a nucleophile is shown here which is attacking C plus center, which is electron deficient. An electrophile is an electron deficient species which can accept electrons and is attracted to regions of negative charge or electron rich sites. They are often positively charged or carry a partial positive charge. Some examples of electrophiles are H+, Br+, Cl+, and NO2+. Electrophiles will attack electron-rich regions. Example, NO2+ is an electrophile which is getting attracted from benzene. A benzene ring is an electron-rich region. Bonding in organic molecules. Hybridization in organic molecules. Each carbon atom has 4 electrons in its outermost shell, which has the electronic configuration 1s2, 2s2, 2p2. Carbon atoms share these 4 electrons in 4 covalent bonds with other atoms to achieve a full outer shell electronic configuration. These electrons are found in orbitals within the respective atoms. When forming a covalent bond, the orbitals overlap in such a way to form 2 types of bonds, sigma bonds and pi bonds. As you can see here, hybridization is the mixing up of different atomic orbitals, resulting in new orbitals of equal energy. Carbon's electronic configuration in ground state and excited state is shown over here. In sp3 hybridization, all orbitals mix to form 4 sp3 orbitals. In sp2 hybridization, 2s, 2px and 2py mix to form 3 sp2 hybrid orbitals, which has got 1 pure p orbital, while in sp, 2s and 2px mix to form 2 sp hybrid orbitals and you have 2 pure p orbitals. In sp3 hybridization, carbon atoms that form 4 sigma bonds are said to be sp3 hybridized. The molecule adopts a tetrahedral arrangement with bond angles of 109.5 degree. This diagram shows a molecule of ethane in which each carbon atom forms 4 sigma bonds to adopt a tetrahedral configuration and minimize the repulsion between the bonding pairs of electrons. sp2 hybridization. When carbon atoms use only 3 of their electron pairs to form a sigma bond, they are said to be sp2 hybridized. When the p orbitals of 2 carbon atoms overlap with each other, a pi bond is formed. The two orbitals that form the pi bond lie above and below the plane of the two carbon atoms to maximize bond overlap. The three bonding pair of electrons are in the plane of the molecule and repel each other. The molecule adopts a planar arrangement with bond angles of 120 degrees. The overlap of two p orbitals results in a bond. Ethene is described as a planar molecule. All the carbon and hydrogen atoms in the ethene molecule lie in the same plane. The two carbon atoms are said to be in sp2 hybridized. sp hybridization. Carbon atoms can also use only one of their electron pair to form a sigma bond, in which case the carbon atoms are said to be sp hybridized. When the four p orbitals of the carbon atoms overlap with each other, two pi bonds are formed. This maximizes the overlap of the four p orbitals. The molecule adopts a linear arrangement with bond angles 180 degrees. Example, ethine. The overlap of four p orbitals resulting in two pi bonds in ethine. Ethine is described as a linear molecule. The two carbon atoms and both hydrogen atoms in ethine molecule lie in a straight line. The two carbon atoms are said to be sp hybridized. The next subtopic is isomerism, existence of two or more compounds with the same molecular formula but different structural formula. Isomers can be classified into two, structural and stereo. In structural isomers, molecules that have the same molecular formula but have a different arrangement of the atoms. The types of structural isomers are chain isomerism, position isomers, and functional group isomers. Stereoisomers are molecules that have same structure but different spatial arrangement of atoms in 3D space. Two types of stereoisomers are geometrical and optical. Let's see chain isomers. Isomers have different carbon chain length. Same chemical properties but slightly different physical. Example, butane and methylpropane. Position isomers. Isomers differ in position of substituent atoms or group or the functional group. Same chemical properties but slightly different physical. But1 in and but2 in. Functional isomers. Isomers have different functional groups, belong to different homologous series, have different physical and chemical properties. A ratio of carbon is to hydrogen is shown here for different functional groups and example. The first one, carbon and hydrogen is 1:3 ratio. Functional groups can be alcohol and ether. Example, C2H6O. If the ratio is 1:2, the functional groups can be aldehyde and ketone. Example, C3H6O. If the ratio of carbon and hydrogen is 1:2, then it can be either carboxylic acid and ester. Example, C3H6O2. Examples of functional group isomers is shown here. Given the molecular formula C3H8O, we can draw both an alcohol and an ether. Example, propan-1-ol and methoxyethane. The next type of isomerism is geometrical isomerism or Cis-Trans isomerism. It's shown only by alkenes. Arises due to restriction of rotation of double bond. Only possible when each carbon has two different groups. Cis-Trans isomers have different boiling point. Cis isomers have higher dipole. Trans isomer of symmetrical alkene have zero dipole. Example is shown here. Molecules with restricted rotation about the CC bond can have geometrical isomers. This includes unsaturated and cyclic compounds. Cis isomer has both of the highest priority groups on the same end. Trans isomer has the highest priority groups diagonally across from each other on the opposite sides of the double bond. The priority of the groups is decided by the atomic number. For the isomers below, the highest priority group on the left side is a methyl group. CH3, and on the right side it is the ethyl group CH2CH3. Cis-pent-2-ene and trans-pent-2-ene is shown over here. Another example, cis-3-methyl-cyclopentanol and trans-3-methyl-cyclopentanol. We can also show the two cis-trans isomers more clearly from a side view. The first one, both CH3 and OH groups point upwards out of the paper. The second one, CH3 group points upwards, whereas the OH group points downwards, trans isomer. The next type of isomerism is optical isomers. This arises from different arrangement of atoms or groups in 3D space, resulting in two isomers, have effect on polarized light. There should be chiral carbon atom, which is a carbon having 4 single bonds and 4 different atoms or groups. Isomers are non-superimposable mirror images of each other. They have same physical and chemical properties. A number of optical isomers in a molecule containing n chiral carbon atoms is 2 raised to n. Example is shown here. The two different optical isomers are also called enantiomers. Types of organic reaction. The first reaction is addition reactions, which involve the formation of a single product from 2 or more reactant molecules. An example is the addition reaction between an alkene and bromine. C2H4 plus Br2 gives C2H4Br2. The next one is elimination reactions, which result in the removal of a small molecule from a larger reactant molecule. An example is the dehydration of an alcohol by concentrated sulfuric acid. C2H5OH in presence of concentrated sulfuric acid gives C2H4 plus H2O. Condensation reaction, a reaction in which two organic molecules join together and in the process eliminate a small molecule such as water or hydrogen chloride. Substitution reactions involve the replacement of one atom or group of atoms by another. For example, the free radical substitution of alkanes by chlorine in sunlight. CH4 plus Cl2 in presence of UV light gives CH3Cl plus HCl. Here, a hydrogen atom in CH4 has been replaced by a Cl atom. Hydrolysis is the breakdown of a molecule by water. We can speed up this type of reaction by adding acid or alkali. For example, the hydrolysis of a halogenoalkane by water to give an alcohol. C2H5Br plus H2O gives C2H5OH plus HBr. Hydrolysis with alkali is faster and gives slightly different products. C2H5Br plus NaOH gives C2H5OH and NaBr. Oxidation reaction, the addition of oxygen, removal of electrons, or increase in oxidation number of a substance. In organic chemistry, this refers to a reaction in which oxygen atoms are added to a molecule or hydrogen atoms are removed from a molecule. An example is the partial oxidation of ethanol to ethanal using acidified potassium dichromate 6 solution. C2H5OH plus O gives CH3CHO plus H2O. Before the reaction, ethanol contains 1 oxygen atom and 6 hydrogen atoms. After the reaction, ethanol contains 1 oxygen atom and 4 hydrogen atoms. In effect, the ethanol loses 2 hydrogen atoms, so we can say that ethanol has been oxidized. Reduction reaction, the removal of oxygen, addition of electrons, or decrease in oxidation number of a substance. In organic chemistry, it is the removal of oxygen atoms from a molecule and or the addition of hydrogen atoms to a molecule. For example, in the reduction of ketone using sodium tetrahydroborate NaBH4, CH3COCH3 plus 2 hydrogen gives CH3CHOH CH3. That's all. Thank you so much for watching this video.